Hey everybody, Dr. White here, beginning Chapter 7 on techniques for finding antiderivatives. We already know one good technique, U substitution, but there's a lot more possible tricks that we might try. And in this section, we introduce one of the most important, integration by parts. Let's get to it by just thinking about the product rule in ordinary differential calculus, Calc 1, and let's just apply the product rule and do some manipulations, okay? So imagine that u of x and v of x are functions of x. Then their product, u times v, would be a function of x, and so it would have a derivative with respect to x, and the product rule for derivatives gives it to us. First times derivative of second plus second times derivative of first. U times dv dx plus v times du dx. Okay. Now what I'm going to do is take this equation and do the indefinite integral of both sides with respect to our variable x. And so I've got the indefinite integral of the derivative of uv, and I've got the indefinite integral of u dv dx plus v du dx. Now, on the left, you can just imagine the dx as a little number that gets canceled by this number here, and then you would have a duv, okay? That's the informal way. Remember from Calc 1, they talk about differentials. This is the informal way that people thought about derivatives when they first developed calculus as a ratio of two very small d numbers, differentials. Now on the right, you could use the sum property of integrals to break this up as to two definite and indefinite integrals, this one here and this one here. All right. Now, what would be the antiderivative of duv? Well, the antiderivative of dx is x, the antiderivative of dy is y, so the antiderivative of d anything is that thing. So I'd get a uv on the left. Haven't done anything to the right in this step. But in the next step, I'm going to again pretend that those little dx's are tiny numbers that I can cancel in a fraction. And I get the antiderivative of u dv, antiderivative of v du. And I'm going to solve this for the antiderivative of u dv, getting this little formula here, which I can pronounce. Integral of u dv is uv minus integral v du. Integral u dv is uv minus integral v du. Pronounce it to yourself a lot. Write it down, commit it to memory. This is the so-called integration by parts formula. But what in the world is it good for? Well, let me give you an example. Suppose you needed to find the indefinite integral for x times cosine of x. The big challenge is just to find one antiderivative, And, the problem is this is a product, but there's no product rule for antiderivatives. There's a product rule for derivatives, but not for antiderivatives. So you can't just leap in and say, oh, it must be x squared over 2 times sine of x, just taking the antiderivative of the x, the antiderivative of the cosine x. You just can't do that. So, but what if you could recognize this as this somehow? Then you could say it's this. And you could hope that this remaining indefinite integral is easier to find. Let's see if we could do that. To do that, we would have to choose a part of our problem to be the u and the rest of the problem to be the dv. So looking into here, I'm going to make a choice. This is the inventiveness, the creativeness of it. The choice is up to me, and some choices are helpful and some of them are not. But I'm just going to make the choice to let u be the x bit of that. And so then I'll have to let the dv be the rest of it, cosine of x dx. Okay? So I've made these choices here. Now, in order to recognize it as this other side, I'm going to have to find the v, and I'm going to have to find the du. So let me head down here, and after I've made my choice, let me find my v and find my du. So let's see, I know dv. So v must be the antiderivative of dv, antiderivative of cosine of x dx. That would be sine of x plus any number. I only need one antiderivative here, so I'll just write a sine of x. Now, what about the du? Well, u is x, so du dx would be 1, so du would be 1 times dx, or just dx. Okay, now thinking back to our formula, this is uv minus integral v du. So let's write this in. Well, let's see. U is x, put that in. V is the sine of x, put that in. And then I've got to do minus the integral of my v, which is sine of x, times my du, which is dx. And I hope that this indefinite integral is easier to find, and it is, because the indefinite integral of sine of x is a minus cosine x, tack on a plus c to, just have a whole family of them. And so I've got x sine x minus cosine x sine x plus cosine x plus an arbitrary constant. Wow. Integration by parts can be really powerful, really, really powerful. And it's an idea that should especially occur to you when your integrand looks like some kind of product. Okay? The general strategy for making a good choice for your u and your dv is to remember, first of all, that the whole problem has to come out to the u times dv. So together, the u and the dv got to make up everything. And beyond that, you generally want to let u be what I might call an auspicious piece. Auspicious means bringing good fortune. Yeah. An auspicious part of the problem. One that would not be too hard to differentiate. Okay? The dv, once you've chosen your u, the dv is going to have to be everything else, including the dx. Okay? But the dv should not be too hard to find an antiderivative for, because you're going to have to go and get the v out of the antiderivative of dv. Okay? And then hopefully what will happen is that the integral of v du will be an easier integral problem than the integral of u dv was. That's your hope. So let's try it again on another example and see how it works out. This is an example where when you do integration by parts the first time around, you do get an easier looking problem, but it's still kind of tough. And it turns out if you do integration by parts again on the resulting new integral problem, then you can solve the thing completely. So let's take our example. It's the indefinite integral of x squared times e to the x dx. So that's clearly a product. Why don't we let u be x squared? After all, it would be pretty easy to get the derivative of x squared. dv is going to have to be everything else, but it's not so hard to get the antiderivative of e to the x. In fact, the antiderivative of e to the x is e to the x. And the du is 2x dx. So we take that and we use our integration by parts formula. Here is our u, and here is our v, minus the integral of our v, a du. And I pulled a constant out, and I kind of stare at this new problem that I've got. And that's still hard. I can't like immediately think of an antiderivative for that. But it's a product, and my thought might be to do integration by parts again, but this time I'm going to let u be the x and the dv be everything else. Once again, the v will be e to the x. This time du will be just dx, derivative of x being 1. And so when I take this whole expression and I substitute in what the integration by parts formula says is going to be this piece here, then I get all this. Here's my uv minus my integral v du. And I work through with the algebra a little bit. And I stare at what I've got. That one I know right off. Antiderivative of e to the x is e to the x. So if I just tack on a plus c, I've got the whole family of antiderivatives for the original problem. Great. So sometimes you use integration part by parts but more than once. And like quite often it'll happen to you. It's like beating down something, it's tough, then it's a little less tough, then a little less tough, and finally it's easy. Sometimes integration by parts works even when you think it doesn't even make sense to try. This is called the taking dv equals dx trick. They talk about it in the book that way. Say you have to do the antiderivative of log of x, okay? Well, it doesn't look like there's a product there at all. But why not just take u to be everything except the dx? So dv would have to be dx. The cool thing is the integral of dx to get the v is just like the integral of 1 dx, and that would be x. So the v is easy to find. And look at the du, derivative of log of x, 1 over x times dx. This is really cool. When you go to the uv minus the integral of v du, those x's cancel away. And you just have the integral of 1 dx, which comes out to an x. And so we've got an antiderivative. Wow, tack on a plus c, and we have the full family of antiderivatives that make up the indefinite integral here. So this is actually so important and useful. Everybody wants to know the antiderivative of log of x. And remember, it's x log x minus x. That's worth just memorizing. Now, I talked about how you might have to do integration by parts more than once from time to time. And sometimes when you do it, it seems like the new problem is not any easier than the old problem. And sometimes when you do it, it seems like you're just going to get totally stuck. But you're not, and sometimes you will be. Sometimes like there's no hope for you. But not always. Watch out for the opportunity to snatch victory from the jaws of defeat. Look at this problem here. Integral e to the x cosine x dx. All right, I'm just going to let u be cosine of x, let dv be everything else, u to the x dx. Just see what happens. So v is the antiderivative of e to the x dx, that's e to the x. Du would be derivative of cosine is minus sine times dx. Head up to integration by parts, uv, which I just conveniently wrote. I decided to write the u here and the v here because it looked better. Commutativity of multiplication, I can do it. Minus the integral of the v, which is here, times the du, which is here. And do some algebra. Minus minus is a plus, and now I'm staring at this integral, which does not look any easier. It's a little bit different. It's got a sine of x instead of a cosine of x, but it doesn't look any easier. So I'm a little worried over here. But I'll try integration by parts again on that new integral. I'll let u be sine of x. I'll let dv be e to the x dx. So v is e to the x again, and du this time is cosine of x dx. And then I'll just replace this with what integration by parts says it is. Here's my uv, written as vu, minus the integral of the v du. And so I stare at this thing and oops, that's like my original problem, you know? So this looks really bad. It looks like I'm really stuck because if I did integration by parts on this again, I would end up coming to this kind of problem and do it again, and I would come back to, this kind of problem. I would just keep on circling around forever. So it looks like I'm really totally defeated here, that I should hope that there's some other integration technique that might help me to find an antiderivative for e to the x cosine x. But wait, take stock of things. When you look at this, you're saying this unknown thing is equal to this stuff, which is equal to this stuff, which is equal to this stuff, okay? Therefore, this unknown thing is equal to this stuff. Transitivity of equality, they used to call it back in grade school. So you've got this equation. Unknown thing is all this stuff. It's an equation that involves this unknown thing. Here it is here. Here it is here. Just like any equation with any unknown, like an unknown x back in high school algebra, you can try to solve that equation for the unknown. And so I'm going to try to do that. So I look at this equation and I think, what if I added antiderivative e to the x cosine dx to both sides, okay? On the left, I'd get twice my unknown antiderivative. And on the right, I'd get stuff involving x that I know. And if I divided both sides by 2, I'd have my unknown is 1/2 this stuff that I know. Great, that would be an antiderivative for e to the x cosine x. Tack on a plus c, and you get the family of all antiderivatives that makes up this indefinite integral that you want to find. Wow. So watch for opportunities to snatch victory from the jaws of defeat. You'll also often find yourself doing integration by parts more than once and, gradually beating a hard problem down to easier ones. The books draws your attention to what it calls some reduction formulas. And they offer one in the body of the text, and they offer some other in the exercises. One that they offer in the textbook is, what if you have to find the antiderivative of sine of x raised to the nth power, where n is some, positive whole number. You could actually use integration by parts to express it like this, where your integral now involves sine to 2 less of a power. And that's proved in the textbook using integration by parts. Here's another reduction formula. Antiderivative of x to the n e to the x is x to the n e to the x minus n times antiderivative of x to 1 less power e to the x. Let's prove that one and then use it, just to show you that these reduction formulas are nice to work with. So if I'm looking at x to the n e to the x dx, I could choose u to the x to the n, and dv is everything else. V is e to the x. Du would be derivative of x to the n times x to the n minus 1 times dx. Here's my uv minus my integral of v du. Pull out the constant of n, stare at what's left. Oh my goodness, we've done it. That's the other side of the reduction formula. So how might you use this? If you get like this, antiderivative x cubed e to the x dx, you could do integration by parts. You'd have to do it like 3 times to make it work. But you could also use this reduction formula, and that might save you a little time and confusion. Let's try the reduction formula. X to the n e to the x minus n, x to integral of x to 1 less power dx. Got to use the reduction formula on that. So these parentheses here contain this, with the reduction formula applied, x to the n e to the x minus n, integral of x to the 1 less power, okay? And then let me see, I'll take this and I'll just do some arithmetic, work some minus signs through and multiply a bit. And I've got this problem. And I've got, looking at that integral, I could apply the reduction formula to that, where the n is 1. And so I have x to the n e to the x minus n, integral x to 1 less power e to the x. And of course, x to the 0 is a 1. And so I do my algebra again, just to simplify things out. And I still have this integral of 1 e to the x dx. But I know that right away. The antiderivative of e to the x is just e to the x. So if I tack on a plus c, I've got the full family of antiderivatives. Great. Reduction formulas can be very convenient. What if you need to do definite integrals of some tough integrand? No problem. You can just look for any antiderivative and apply the fundamental theorem of calculus. Well, here's an example where maybe you have to do integration by parts to find your antiderivative. What if you need the signed area under the curve tangent inverse x from x is 0 to x is 1? Well, let's first concentrate on just getting an antiderivative. So I'm going to consider the indefinite integral version of the problem. Just ignore the limits for now. And I'm going to try that kind of desperation technique of don't see a product. I'm going to let u be the tangent inverse x and let dv be just the dx. So v would be x, and the derivative of tangent inverse is 1 over 1 plus the x squared. So du is this, the little dx at the end. So here's the v is the x, the u is tangent inverse x. That's my uv, minus the integral of the vx times the du, which is this dx over 1 plus x squared stuff. And so I stare at that and I realize, I could maybe try u substitution. I could let u be 1 plus x squared. So this is not integration by parts. This is just regular old u substitution from the previous chapter. Du would be 2x dx, so dx would be du over 2x. And so when I take this and plug in u's wherever I can, I get this. The x's cancel, the half comes outside, and I'm looking at this problem. But the antiderivative of 1 over u is the log of the absolute value of u. So my whole thing turns out to be this. Now I'm looking at the log of the absolute value of 1 plus x squared, and I think to myself, 1 plus x squared is always a positive number. So it'll be equal to its own absolute value, so I don't have to have the absolute value signs there. I can drop them. Always look for opportunities to do that when you're working with absolute values. So if I were to add on a plus c, I'd get the full family of antiderivatives. But I only need one antiderivative in order to apply the fundamental theorem of calculus. So here I am wanting that definite integral. I take my antiderivative and I evaluate between the x is 0 and the x is 1. So when x is 1, I get this stuff. 1 times inverse tangent of 1. Then minus the half log of 1 plus 1 squared. So that comes out to log of 2. And then this stuff is where I've plugged in 0 for my x. And you can see I'm going to get nothing out from this first term. And log of 1 is 0, so nothing's coming out from there. It's all coming from here. Now, tangent inverse 1. So I'm looking for an angle whose tangent is 1. Well, that would be an angle where the sine and the cosine are the same. What's the simplest angle where that happens? Pi over 4 radians. So this is pi over 4. And here I've got a log 2 over 2. So I'm done. There's the signed area underneath tangent inverse of x. Okay, that's all the examples that I wanted to try right now. See you later.